Welcome back. In lecture 35, we will start with trip distribution. The different concepts that would be covered in this lecture are on trip distribution, the basics, and then we will talk about the gravity model, and we will talk about a few growth factor models. So, trip distribution is the second stage in the sequential 4-step table demand forecasting model. So, after we have estimated number of trips produced and number of trips attracted in a particular from different zones in an urban area, we can estimate the total number of trips that starts from one zone and then ends at another zone. So, this flow of trips between different zones is known as trip distribution. So, trips generated from each zone is distributed to all other zones as per the choice of destination. Now, the destination choice, how people decide on their destination choice, that is there are different ways to determine that, and trip distribution actually lists several methods which could be used to determine this destination choice. Now, as we have discussed earlier in residential location choice, so similar to that residential location choice model, we can also have a destination choice model or even joint models of mode and destination choice or even destination and route choice. So, this kind of complex models could be also developed, but at the same time when we are talking about entire city and then we have got, suppose the city has got 200 zones. So, from 200 to 200 zones, so these are if people start traveling from each zone to each zone. So, we will have around 200 multiplied by 200 so many flow data values. So, that means Tij or values will be around Tij means trip starting from zone I and ending at zone j. So, we will have around 200 into 200 number of Tij values. So, in that case the number of destination choices for a particular zone will remain, of course, there will be 200 choices from for a particular person to choose from, and that may be difficult to ascertain because we have to do it for different kinds of trips. We may even have to do it for different socioeconomic groups. So, this makes it more complex, but that could be adopted for some kinds of trips, and that is also done in some models. But basically when we talk about trip distribution, we actually want to look at more simpler ways, so that we can do this exercise for the entire city and in such a way so that it matches the existing data, that existing flow rates that we observe, and as well as we can also take care, we also need to have some methods so that we could also estimate the number of trips which are flowing out from the surrounding areas and so on into the city area. So, if you see in the particular figure, so first we start with trip production. There are 3 zones and we have got productions from each zone, and then we have trip attractions from 3 zones. So, zone 1 attract 30 trips, zone 2 attract 50 trips, and zone 3 attract 40 trips. So, if I add both this up, this comes to around 60, 70, 80, 90. So, 120. So, both number of trips produced and number of trips attracted is 120. So, now if I add them up and if I distribute them over in a matrix, where on this side we have number of trips going towards different zones, and over this side we have got number of trips produced at different zones. So, if I add all this up, like number of trips produced from 1 and going to zone 1, then this is 10, this is again going to zone 2 is 10, and then going to zone 3 is 5. So, if I add them up, that is 25. So, this 25 matches with this particular 25. Similarly, if I add up the row number 2, there I get around 50, 65 trips, and so on. So, in this way, if I add the row totals give me total number of trips produced at different zones, whereas the column totals give me the number of trips attracted at different zones. So, over here number of trips attracted at zone 1 is given as 10 plus 15 plus 5, that comes to around 30. So, in this way we can form a trip distribution matrix, and this matrix could be used further down the line, where we have the third stage in the 4-stage sequential travel demand forecasting process, which is the mode determining mode choice for each trip. So, for each zone to zone flow, that is, for example, for this particular flow which is starting from zone 3 and then ending at zone 2. So, we have got 15 trips, then it is again we have to estimate a mode choice model where we will determine how this 15 trips should be distributed between different modes. So, mode 1 there are 5 trips and mode 2 there are 10 trips, and finally, this particular trip, suppose this one is bus. Now, we have to assign these bus trips to different routes or different pathways, so that these pathways would be used to reach a particular zone. To of course, they will be able to reach, people will be able to reach from zone 3 to zone 2, and that actually shows route A there would be 5 number of people using transit or bus, and then in route B, this is bus route B, then there are 2 people, and then bus route C there are 3 people. So, in case of car, we can say route A is the shortest route, this is shortest route between the first shortest route, the route B could be the second shortest route, and route C could be the third shortest route, or it could be in any order. So, we can see this is the distribution, these are 3 routes which could be used to reach between these 2 points, and this is how trips would be distributed. So, this is the basic concepts of trip distribution. Now, there are different methods to go ahead and distribute trips in an urban area. Once we have total number of trips produced and total number of trips attracted for each zone in an urban area, or each TAZ we can also call. And so, there are different methods. So, this actually lists the different methods. For example, within the growth factor method, as you can understand from the term growth factor, that means existing number of trips traveling between zone I to zone J is multiplied with some form of a growth factor, and we get the new number of new trips. So, that is the basic idea behind growth factor method. So, there are different growth factor methods like uniform growth factor method, average factor method, Freita method, furnace method. So, we will look at some of these growth factor methods. And then there are synthetic methods as well, where existing data Tij values and production attraction values are analyzed, and using this data we determine some relationships based on certain principles, and using these relationships we can develop the trip distribution of a future year. That means, we are using the base year data, we will be able to predict trip for a future or a predicted whichever would be your prediction period. As per that, we can also predict the trip distribution for a future time period. So, some of the popular models in this particular within the synthetic methods are gravity model, which is the most famous one, and then there is Tanner model, then there is intervening opportunities model, then competing opportunities model. And so, in this particular lecture we will be looking at gravity model, which is particularly it is the most common form of model which is used for determining trip distribution for internal trips, and growth factor model, which is particularly used for external trips, that is trips coming from the surrounding area into this particular urban area that we are investigating. And because these trips are coming from surrounding areas, we are not sure from how far they are coming in. So, we are not sure about their impedances or the travel time they take to come inside the urban area. We just have overall estimates of maybe population for this particular zone, or we can even have estimates for the growth in a future time period for this particular zone. Based on that, we can estimate the total number of trips produced in those zones in future, and from that we have to estimate how many of those trips would be coming to this particular urban area also in future. So, trip distribution using both these classical models, gravity model as well as the growth factor model, this is undertaken separately for different trip purposes. So, we will do trip distribution for walk trips, we will do trip distribution for business trips, we will do trip distribution for school trips. So, each one is separate, because as you can understand, each of these purposes require are based on the land use, they are at different parts of the city. So, if we use the same way to distribute trips, then they may give us very erroneous results. So, that is why we categorize the trips into different purposes. So, trip distribution is also sometimes undertaken as per household socio-demographic characteristics. Why? Because if you understand the 4 stages, that means we start with production, and production attraction of course, and then trip distribution, then the mode choice, and then the route choices and so on. So, in the mode choice part, we actually require data which shows us that different types of socioeconomic groups or belonging to different economic categories and so on, people would be choosing different modes or they are prone to choose different modes. So, we need to bring to that particular in the mode choice level, we need to bring the trip distribution data in a form which is also taking care of the socioeconomic characteristics. So, that is why if I have done it just based on trip purpose, then I would not be able to say how many of these people who are traveling from I to j for trip purpose work is belonging to which socioeconomic group. So, that is why if I have divided the data into previously into different socioeconomic groups, then based on work purpose, different trip purpose, we have done the distribution. Probably we will end up with overall trip matrices, OD matrices we call them, in such a way, so that that could be used in a mode choice model which can utilize this socioeconomic data set. So, this is the trip distribution two matrices that we use. The first matrix, as you can see, this we have the zones. So, in this side we have the destination zones 1, 2 until n, and we have these are the these are the destination zones and these are the origin zones 1 to n. Now, over here that means T11 is the number of trips originating at 1 and ending at 1, and this one is number of trips originating 1 and ending at 2. So, if I add them up, this is total of total number of trips originating in zone 1, and if I add them up this way, then total number of trips destined to zone 1. So, this is how the trip OD matrix is. So, we call this a origin destination matrix. And next we also have something called a scheme table, which is base year and target year interzonal impedances. So, these are the data set that we require. So, usually the base year data set we know because we have done surveys in the urban area. So, we can estimate the T11 values. This actually means the total travel time taken from zone 1 to 1, or it could be total travel cost. Any form of impedance could be used. So, this matrix actually gives us the total impedance from one zone to another. Now, the thing is based on survey data, we can get base year matrices. For target year matrices, we may keep it as same, or if a new mode is added, or there are certain changes we expect in the network, then we can also change the final target year trip matrix. So, or sorry, the impedance matrix. So, this actually whenever we are using any kind of model, we have to actually when we are doing the prediction, we have to use the target year interzonal impedance matrix instead of the base year impedance matrix. Whereas, when we are developing the model or calibrating the model, then we use the base year matrix. Interzonal impedance is obtained from existing and proposed networks and mode availability data. So, that means existing and proposed network both are considered, and then mode availability data also is required, because that actually determines that which are the modes we are going to consider if we are going to create a composite matrix of travel impedance between different zones. So, this is what we need to consider. So, we can summarize by saying that the total number of trips attracted to a particular zone is summation of all trips originating in different zones which are attracted to zone j, and similarly all trips originating in zone I is a summation of all trips originating in zone I and ending in all the other zones j, and so total summation of dj is equal to summation of oi. So, this is what is the basic constraints that we use, and because we have constrained the model from two sides, that is from the destination side and also from the origin side, it is called a doubly constrained model. Whereas, if it was we know only one, that means we do not know the other, we know that total number of origins in now and total number of origins in future, we do not know the destinations. In that, we will call it a singly constrained model, where either trip production origins or trip attraction destinations are known. So, if in those cases we or if both are known, then we can call it a doubly constrained model. So, whenever we are developing the trip distribution model, so we see that first when we need to predict the target year interzonal calibrated, we want to predict the target year Tij values. For that we require the target year production and attraction values, and also we require the target year interzonal impedance values, and these two values are put into a distribution model, a calibrated trip distribution model, and then in that calibrated trip distribution, this is basically a set of equations where we will put this data, and then we get the final target year trip distribution data. So, whereas this calibrated trip distribution model is actually developed based on base year production and attraction and base year interzonal impedance. So, this is what I explained in the last slide as well. So, this is how we develop this trip distribution model. So, interzonal impedance, as I was telling you earlier, that it could mean travel time, it could mean travel cost, it could mean inconvenience cost, it could be parking, and it can include parking and toll cost, it can include car travel time, it could include transit travel time, or it could be a combined travel time of different modes, or it could also include in vehicle travel time, access time, waiting time, transfer time, and so on. So, any kind of cost or impedance could be included in the interzonal impedance functions that we use, and we can go for a generalized cost, which is a composite index, which can include all the different parameters and can create one value of impedance for each particular interzonal flow. That is, for each Ij value we can get one composite index score for generalized cost. And some models nowadays can also use something called a composite utility instead of a composite index or a score, which actually is based on the modes available to this particular zone, and we use the log sum variable from mode choice model. So, basically if you remember from discrete choice, we have several alternatives to choose from, and that means the probability of choosing one alternative is equal to the utility of that alternative divided by e to the power utility of that alternative divided by summation of e to the power all the other alternatives, utility of all the other alternatives. So, this denominator term is the log of the denominator term is called the log sum variable. So, this is what we can also use, which also gives us a composite utility measure for all the modes that are available or all the alternatives that are available for that particular Ij value. So, the first model that we will explain is the gravity model. This is based on Newton's law of gravitation. We have already explained this model earlier as well. So, this is a model where the total number of trips Tij, which is also known as the interchange volume, is determined using this particular formula, where k multiplied by Oi into dj divided by Wij to the power c. Now, k and c are the model parameters, and we need to estimate this particular model parameters, and this is done by the process of calibration of the base year data. C is the exponent of the impedance term, and it is usually assumed to be 2, but can be also estimated through calibration. So, it can assume other values as well. So, this is one form of impedance we have already seen during the accessibility lectures, and we also know that Oi is equal to summation of Tix, and x is basically all the other destination zones. So, that means all trips originating from I and ending at all other zones. So, we have seen that. Now, if I replace this Tix using this formula, then we get this particular form. Now, here Oi and Oi cancels on both sides, and we can also determine the value of k, which is equal to 1 divided by this particular part. So, that is what is being shown here. Now, this gives us the classical form of the gravity model. So, this is the classical form where Tij is equal to Oi into, we get dj divided by Wij to the power c divided by summation of dx divided by wix c, and x is starting and all the different destination zones that we are considering. So, this value actually is going at the impedance, because k is equal to 1 by this 1 by this particular value. So, this is coming over here, and dj divided by wicj, this remains over here. So, this, if I look at this particular form, you see this is a proportion of trips originating, this is the number of trips, a proportion of that at zone I and destined attracted to zone j, considering attraction of all other zones. So, we have dj divided by all other zones that means the attraction, and this attraction is also weighted by this calibrated this impedance function as well. So, that is how we can determine that OI Tij is a proportion of all trips originating at OI, and it is as per the proportion of destination the total number of trips attracted to different zones. So, this is similar to accessibility of a zone. This we have already seen, this kind of measures we have used in accessibility, and thus we do not require absolute trip attraction values, just relative attractiveness. Because it is a proportion, we just want to know what is the proportion of trips going to a particular zone instead of actual figures. So, that will also help us to estimate this particular model. So, trip attraction values are not that important. Generation we need to know, attraction we just need to know the relative share of the attraction. So, the other form of the gravity model is this, where everything remains same, only f 1 by wij to the power c is replaced by fij. Now, this is called the travel time or friction factor. So, when we do the calibration of the gravity model or this particular c value and all, then actually we have to calibrate the f, this particular value, fij value needs to be calibrated. So, why is calibration required? Now, we said that we will start with wij value equal to c. Even though we start with that, we will see that at the end of the trip distribution using this particular formula, the total number of trips that does not match with the total number of trips attracted and total number of trips generated will not match. So, that is why we need to calibrate the model through a process, so that it actually matches with the actual trips that are produced or attracted to a different total number of trips that are attracted or produced should match. So, even after once we have done this, so after we have calibrated the model, even so the model may not match. In that case, we can add another factor which actually instead of fij is one impedance factor, which is a which gives the characteristics of impedance to this particular zone, but there may be many other reasons why the trip distribution does not match. Because trip distribution is not only a function of impedance, there may be other related factors. Like for example, if we have not considered job matching, that means we are doing general trip distribution for all work trips. We are not doing for a particular segment of employees and a particular segment of jobs. So, in that case there would be some differences from zone to zone. So, that is why we need to include another calibration, another factor which also could be calibrated or determined, which takes care of all these unobserved factors influencing trip distribution. So, that is why we introduced this new factor Kij, and the same way we have done Fij at the top, we can also include Kij, and that also goes in the denominator term. And finally, we can write OI is equal to Pij, where Pij is the probability of trip originating from zone I that will be attracted or destined to zone j. So, we have to determine this Fij and Kij values eventually. So, let us first see the application of a gravity model. So, we have a scheme table which is interzonal impedance, it could be anything, cost, time, anything. So, we see these are the destinations and these are the origins on this side, and we have zone 1 to 5 and again 1 to 5 over here, and zone 1 to 1 impedance is 5, 1 to 2 impedance is 10, zone 2 to 1 impedance is 10, more or less in this case we have taken the impedance as same in both direction. Now, suddenly we see 1000. Now, we could have put a 0 over here, that means there is no impedance, there is no value, that means nobody travels from here to there. But for consistency in estimates, because sometimes impedance goes at the denominator, impedance is going Wij value is always 1 by Wij, even though we are taking Fij, sometimes we could have used a form where we have taken 1 by Wij. So, they are dividing by 0 will result in problems. So, instead of 0 we take a very high figure, which could be 10,000, 20 or 1 lakh or even more than that. And if I put that as impedance, that means compared to all other zones, it has got so high impedance that we will not find any trip in that particular interzonal from that particular zone to that particular from this 2 to 4 we will not find any trip. So, this interzonal volume would be missing. So, this is how we designate this missing values or or values which are not present, or those connections are not present, those links are not there. So, from the impedance we estimate the friction factor assuming C equal to 2, which gives us all these figures, and you can see these values are very low that we are getting over here, and these are the target year productions over here, and attractions are given in it is just a value is given, we can take relative, this is a relative measure or relative attractiveness of the different zones. So, it is not absolute values, we can take the relative attractiveness values as well. So, in this table we have taken for OI to OJ, that means this is total number of trips originating at I, which is 2000. This is the total number of zones 1 to 5, and we have dj is equal to 0 to 3, this is the relative attractiveness, and we estimate Fij values, the impedance values that we have already estimated earlier. Then we multiply dj into Fij into Kij, we assume Kij equal to 1, and then we get this particular values, we sum it up, we get the summation value over here, and then we determine Pij by just this is the proportion, this is dj for each zone, we can multiply dj into Fij into Kij, which is 1, and divided by this particular value, we get these are the values. So, total this is a proportion, so it will come to 1, and then finally, we multiply proportion with total number of trips originating, we get the actual estimates. So, this is the total number of trips flowing from zone I to zone J. Zone J is 1, zone 2, zone 3 and so on. This is zone 1, and similarly we can have we can do it for the different zones and we get this figure. Now, suddenly we see that this was supposed to be 2500, this is the total number of trips originating. So, when we add up to Tij, it should also be 2500, but it is not matching. The reason is because there are so many terms which needs to be round up, sometimes it may lead to this. Now, think of this when we have got a table of 400 by 400 zones, and there is round up in many areas, and then actually depending on at which stage you are doing the round up, you may end up with figures which are pretty high. So, we also need to be we should take care of this particular problem which may arise in some cases. So, finally, we come to zones, this is the production attractiveness table that we have seen earlier, this is the results that we have got. So, this is the origin destination matrix or interzonal trip table, this is the results of our estimates, and so we have modified the 2500 by reducing this particular term 1268 we have estimated. We found that it was getting round up margin because a little bit excess value over 5. So, we have taken it as 1267 and we have adjusted the figures and we have matched the total number of trips originating and total number of trips attracted. And so, we can we see that predicted interzonal trips may not match survey values when gravity model is estimated with base year data and C equal to 2. And this here it is matching, but it may not match, and then there is a need to calibrate the value of C. So, C equal to 2 is not right. So, we need to find the actual value of C, and this for this we actually calibrate the friction factor F instead of calibrating the value C, which is 1 by Wij C. So, instead of calibrating C, we calibrate the overall friction factor F. Now, let us see how we do that. Now, calibration of gravity model is an iterative process. So, the first step we will start by estimating the value of C as 2 and then estimating all the link volumes Tij are estimated. In the next step what we do is we have a observed data set of Tij values. This is done with the base year data. This right now when the calibration is done using base year production attraction and base year impedances. So, once we have done once we have estimated Tij values using C equal to 2, then we match the histogram or distribution of trips as per different travel times for the predicted values of Tij and the actual observed values of Tij. So, in this particular figure you see there is a observed and there is a result of iteration 1. So, this is observed over here, this is observed. So, if you see this, that means trips which are of travel time ranges of in minutes 1 to 5 minutes, so many number of trips were observed. Trips which are 6 to 10 minutes, so many number of trips were observed. Trips which are 11 to 15 minutes, so many number of trips were observed. So, we divide the entire impedance range into smaller segments, it could be 5 minutes, 10 minutes and so on, and then we find the total number of trips which are there for that urban area and for the both the predicted as well as the for the observed values, and we will see there is a mismatch in these two patterns. So, this mismatch has to be made same. So, that is by changing the value of C, we have to make sure that these two graphs match. So, that is what we do in calibration. Now, how do we do that? So, this results are so what we do is, so we take the friction factor and we adjust its values so that this actually shifts. Now, how do we do that? Now, what we do is we take F star is equal to, this is the new friction factor, which is equal to friction factor into observed divided by calculated. So, adjust F star is the adjustment friction factor at a given impedance, that is for 5 minutes, 10 minutes, 15 minutes and so on, and observed is corresponding percentage of trips during base year and calculated is estimated percentage of trip after iteration 1. So, using that we know that we have to increase this value by so much proportion. So, that is what we are getting over here. So, observed is higher than calculated. So, we get a value. So, that has to be multiplied with f and that will increase my f star value. Now, as you can see this we get for 1 to 5 minutes. So, for each travel time segment we get different f star values. So, f star values are adjusted friction factor at impedance level of 5 minutes, 10 minutes, 15 minutes, 20 minutes and so on. Now, this f star values are plotted against interzonal impedance. Like for example, over here we do not exactly plot f star values, we plot Fij is equal to this 1 by Wij C, we know this formula. So, we take log of f and we also take a log of this side which gives us minus C into log of W. So, we plot this f against this log of W and then we plot this f values, and when we plot this f values we will see that they are on different, these are the points, and this C equal to 2 actually gives us this particular line. So, that means for this new, so this actually may not, this is not matching, that is why we have these different lines. So, we need to take a curve fitting exercise, or we need to find the value of C where this actually fits with this particular distribution of f's. So, that curve fitting exercise is taken, it could be a linear function with a single slope like of C, which is this curve, it will have a slope, that slope is the C value, or it could be something like a gamma function relating f and w. So, it could be a linear function, it could be a gamma function. So, basically it tells us how to adjust this f, or what should be the new f value for this particular set of, or new value which we should use for this particular distribution. So, in this way we can actually determine that we have to adjust our values of C, like over here C equal to 2 give this. So, for a new value we will be able to predict this f values as well, and using that new f values we can actually replot again, and we will see that the new in iteration 2 the values will match with my previous or observed distribution. So, that this is how we can predict the value of C. So, this C is equal to 2 gives us this slope. Now, if I fit another line which is more better fit compared to this C equal to 2, that will actually lead me to get more better values of predicted values compared to the previous iteration. So, in that way the more near predicted, the more better is this particular fit and value of C, more better would gradually be this to fit between two lines, and we will see eventually we will get a perfect fit, almost perfect fit. Now, even though we do this, we will see that even after one or two iterations this does not exactly match. So, there we can actually use this Kij factor, which is estimated for each Tij. That means, for each interzonal volume we have a distinct Kij factor. That means, for this particular zone to zone travel we will have a specific Kij, and Kij is estimated using this formula Kij equal to Rij into 1 minus xi divided by 1 minus xi into Rij, where Rij is the ratio of observed to calculated Tij and xi is the ratio of base year Tij to total production in I. So, this is the formula, and which is specific for each interzonal volume, and this is how we calibrate the gravity model. So, next we come to the growth factor model, where Tij already we have discussed the uniform growth factor earlier, where that means we take a factor f and multiply with all the base year Tijs, and we get the predicted year or the predicted year interzonal Tij value. So, interzonal volume. So, this is one method which is a very simple. Similarly, we have the average method, factor method, and then we have two more methods, Farness method and Frater method. So, we will discuss these two methods. The Farness method is very popular, and this is also very simple. This uses a iterative proportional fitting technique that we have already discussed earlier, and this iterative proportional technique, if you remember, we have this zonal controls. So, similarly over here we have predicted values for trip, we have a table. So, we have a total number of control totals. We used to have control totals on this side and this side. So, over here we have trips, now total number of trips originating from each of these rows and total number of trips attracted in the columns. So, this we have seen. So, similarly we have got prediction year volumes as well, prediction year trip attractions, prediction year trips attractions, as well as prediction year trip generations. And using this this existing year generation and future year generation, or existing year attraction and future year attraction, we create these two factors which is multiplied with the Tij values iteratively, first with this and then with this, and we keep on adjusting like we did in iterative proportional fitting, and then we arrive at the final results when the difference is not that much or it is within the tolerance range that we decide. So, what we do is we introduce these two growth factors Ai and Bj. So, Ai is the proportion between, on this side Ai and this is Bj maybe. Ai is proportion between predicted origin divided by estimated origin, and Bj is predicted attraction divided by estimated attraction. So, first we do it iteratively one by one. So, first we set Bj equal to 1 and we estimate Ai for all the values, and then we multiply with this. Then we get a total for Bj over here, total for trips attracted, which is different from the actual attraction. Then we keep Ai equal to 1 and we change the value of Bj. So, this is a simple iterative proportional fitting method, and this step is repeated till convergence, and as I told you, this estimated error should be within tolerance limit or whatever we set. So, error is measured is equal to summation of all origins minus origin at after total origin I estimated after iteration p. That means target origin, this is the target and this is the estimated value. Means once we have completed the work, not over here it just shows base and target here, but That is how we need to estimate, and we need to do it for all the origins and all the destinations, and we get the total error in estimate, and we can set a target value for that, and as per that we will determine the how many iterations we need to do. So, over here we get the data set for this is zone I and j. There are 5 zones. This is the total number of trips going from one zone to another, total base year origins. This is the summation of all the rows. This is a summation of all the columns. This is base year destinations. So, we get the target year destinations and target year origins over here. So, total number of trips in the target year is 2230. Right now, it is 1815. So, this is the first iteration of the furnace method. You can see we have set Bj equal to 1. We have now estimated Ai, where Ai is proportion 300 divided by 234, which is 1.28, and we multiply this value with the previous Tij values, and we get this particular figures over here. We add them up, we get this new values for Dj, which is different, obviously different from the estimated values. So, in the next step, we fix Ai and we will multiply with Bj, which is estimated again by Dj. This is 1201, this was estimated, and this was the destination proposed. So, 1200 divided by 1201, so this is 92898 and so on. And overall, after iteration 1, we see the total error is 116. So, total trip origins, this is the target and this is estimated. So, we can see this is 17 plus 11 and so on. We can add them up and then also add them up on this side, we get total of 116. So, we will keep on doing this iterations till we reach a value which is acceptable by the analyst. So, furnace method is more appropriate for estimating trip distribution for external trips for an urban area where impedances are not known. So, as you can see in this formula, there is no impedance. Only thing we have got is the target years estimates and the target year estimates, and if I can have this particular predictions for target year productions and attractions, then automatically using this particular method I can also predict target year interzonal volumes. So, finally, we come to the method which is another growth factor method. This is also a popular method which is called Fretter method. So, in the Fretter model, future trips are estimated using this particular equation, where as you can understand Tij is the base year interzonal volume, and Pi by Pi is the proportion of increase between this future trips produced at zone I is Pi, and small pi is total number of trips present trips produced in zone I. So, this is one growth factor based on production, this is another growth factor based on attraction. Now, this production and attraction both are growth factors, and if I multiply with both of them, so we are basically double counting. So, we are multiplying the growth factor twice. So, that is why we introduce another factor which is basically so this will result in higher estimates. So, that is why we use a normalizing factor, which is this particular factor, which basically means sum of all the existing trips out of zone I divided by sum of all existing trips out of zone I multiplied by the growth factor at the destination end of the trip. So, this is the normalizing factor that we have used, and then again through iteration we need to solve these values of Pi and Aj, and with we have this k total number of zones, and we need to keep on iterating when these values match, and then finally we can match the estimated Pi and Aj values, and eventually we come to a result. So, this is the formula that is used over in Fretter model. So, these are the references you can study. So, to conclude, gravity model remains the most popular method for trip distribution. Gravity model is an aggregate model and not sensitive to demographic characteristics. So, if I need to make a model which is characteristic to socioeconomic and other demographic characteristics, in that case I have to develop a destination choice model which is utility based. And gravity model has limited ability to test the effect of change in level of service of available modes, and cannot be used to test policies related to location affecting destination choice. So, this is one limitation of gravity model, and so utility based destination choice models are also gaining ground and widely used in disaggregate studies. Thank you.